Okay. So we'll try to do it this way here. Drag that over there. Okay, cool. So just have a sketchboard up here so we can write some stuff down if we have to. Anyway, starting on page 119, after the first part of the chapter, just talking about some basic inner structure of how the optical equipment works, right? Just looking through a lens and aiming at things and measuring angles that way, which is useful. But like we said before, most of the time now, the GPS is much more efficient as far as being quick and accurate. So it takes the cake in that respect. But it doesn't always take the cake, right? That it doesn't have the ability to do indoor kinds of surveys and things like that. So there are times where you're going to need to use optical equipment, typically a total station. A total station actually comes from the term where the theodolite, if you remember using the theodolite, the one that didn't have any electronics in it, right? The piece of equipment. It was just optical, right? You just turn the lens, you turn the base, and you flip the telescope or whatever, right? So that had no electronics to it. It couldn't measure distance except if you just use the hash marks in the lens. However, it did have some posts on it, if you noticed, that you can attach an electronic distance meter. And we have one that attaches on there, but the battery's dead now. And it's not worth replacing. So what came about with that, just tacking on an electronic distance meter on top of that theodolite became a total station, right? It could measure distance now, and now you could have all kinds of triangle solving that you could do. Like you had a lot more to your disposal. So that's where a total station came in, and then they started making them with, well, electronic, so they could measure the angles electronically and the distance electronically, and then you got yourself, a total solution here. So anyway. Let's go off of some of these cases. So 5.7 on page 119 talks about laying off angles. Okay, so and how to accurately do that. And so we do want to go over that. 5.8 prolonging a straight line. 5.9 bucking in. There's actually a nice little graphic for most of these. Finding an intersection of two straight lines, like two streets or something. Prolonging a measured line by triangulation over an object, like a river or something. Yeah, or just getting past obstacles. What else? 5.12, prolonging a line past an obstacle, going around an object, basically, or around an object. 5.13. Point location, that is, and then that's actually a longer section, and I do want to spend more time in that, because the total station, one of the greatest things in my opinion of the total station is being able to get X, Y, and Z, or northings, eastings, which are Y and X, I guess, and Z, elevation, coordinates, your 3 dimensions coordinates from solving the triangles and stuff. So actually getting the XY, that makes it more like a GPS, and that actually allows you to integrate your data with your GPS data better also. So it's like doing the spreadsheet work where we have the bearings and distances and stuff, and then we calculate from that. You certainly, I don't know if we did that in this class, but we did it in the civil class or whatever, where we got the northings and eastings based on the measurements from the total station or whatever, your bearings and distances and stuff. So what a GPS does, you go out with the GPS unit, it gives you the X, Y, and Z there, and you bring it in, and that's what you use to draw and to make your reports and to do the surveying. So yeah, that's why it's the bulk of the chapter, for that matter. All right, so that is pretty much, it does go over a little bit of data collection using the electronic data collectors. We have one, but it doesn't work. So, and also there is a way, Trimble has an app for your smartphone because the two units that we have are Bluetooth. So you can actually get the data onto your phone, and then you could bring that into the office while you're collecting the data out in the field just on your phone. So that makes it pretty convenient too. Again, GPS is much more convenient. So, all right. Yeah. So back to page, whatever it was, 119, laying off an angle. Okay. There is a figure on page 120 that describes what it says here. So let's just go over it, and then we'll get a feel for how it's described. So, all right. So case one, the angle is to be laid out no more precisely than the least count of the theodolite, meaning, right? So I didn't really look at the owner's manual that closely, but this is the owner's manual for the old one. And somewhere in here, like in the back or whatever, it's going to tell you its accuracy ratio, right? That's the least count. That's the best measurement specification. You know, let's see. Yeah, it gives the length of the telescope, the 150 millimeter lens, which is, you know, a pretty good zoom, 30 times the magnification. Field of view is 1 degree, 30 minutes. Resolving power, where are we going to talk about? Measurement display, no. Here we go, least count in measurement. I don't know if you can see that in there, least count in measurement, not that you care that much, but that's what they're talking about. And this is how it's measured. And this is more important than just knowing well, that's what least count means. When in fine measurement mode, it's 1 millimeter to, let's see, 1 millimeter or 2.2 millimeters. Oh, that's the different models. Okay, never mind. So 1 millimeter, we're going to go with that. There is a model that can go to 0.2 apparently. In coarse mode, 1 millimeter also. So fine and coarse, I guess the least count in measurement is good enough. They're both the same. Tracking measurement mode is 10 millimeters or 0.02 feet. That's its measurement accuracy. What's its angular? Let's see, where is that? Electronic angle measurement right here. Minimum reading. It can compensate for 3 minutes of off-axis tilt. Let's see. I don't even remember what model we're using, but we'll just use the cheapest one here. Yeah, so minimum reading on the GTS, oh, this is the older one, that's why. Yeah, we have the GTS 500, so, or 501. Anyway, 2 minutes is the accuracy standard deviation. No, 1 second, sorry. So it can go to the whole second, in other words. So that's the, that is the best it can read. So that's the most accurate it can be, is up to the whole second. Okay, so just, and every manufacturer is going to have that specification in there, or should be able to look that up. Okay. So the angle is to be laid out no more precisely than that of the theodolite or the total station. Consider a route survey where a deflection angle of 31 degrees, 12 minutes to the right between two consecutive centerline alignments has been determined from aerial photos in order to position the roadway clear of natural obstructions. Yeah, the surveyor sets up the instrument at the point of intersection. Okay, so maybe I'll sketch that out. Let's see how we do with that. All right, so over here we have a line, and here's the point of intersection. Okay, so so this is the back line, right? So over here, your back sighting, right? So you're setting up your station at the PI, and then you're going to back sight to the rod or the prism back at on that back line there. And then you're going to turn an angle. Okay, so well, I'm getting ahead of myself. Okay, so that's what's going on. So 31. So let's see, where am I? Surveyor sets an instrument up at the point of intersection of the two straight line tangents. What that means is the two straight line tangents are what they're going to end up doing is they're going to turn this angle, right? Okay, that's not 31 degrees, but what they're going to do is that's a roadway, so they're going to actually round that off, right? There's going to be a radius there. Okay, but what the surveyor is going to do is just measure where that PI is, and then that could be rounded off, right? Just in AutoCAD, you just use a fillet tool to round that off with the radius, and you're done, right? So it's very useful to just measure to the point of intersection of the two tangent lines, or the two lines going to that curve. So that's the idea behind that. Okay. So here's what they do. So they back sight, they sight back the line with the telescope reversed. So yeah, so pointing in the same direction as the keypad, really. And then and the horizontal circle set to 0. So you 0 set horizontal angle set to 0. Next, the surveyor transits or flips the telescope over and turns the required deflection angle, right? So turns until he gets to 31 degrees, 12 minutes to the right, and set a point A prime, right? So the first measurement, in other words, gets you right here. So they measure, or they when the scope reads 3112, that's A prime. Okay, so because A prime meaning it's not the final result, basically. Surveyor then loosens the clamp, keeping the recorded angle on the scale. That means hold. Sights again at the back line. Okay, so now they're looking back at the back sight, and the angle is still reading 31 degrees, 12 minutes. Okay, and then turns it again, right? So we're familiar with doing this. They're doubling the angle, right? So they should get approximately 62 degrees, 24 minutes. It's very likely that this line of sight will not precisely match the first sighting at A prime. And so if the line does not cross A prime, a new mark, A double prime, is set. So right there. Got another line here, A double prime, right there. Get an eraser. It's not an eraser. It's my problem here. Zoom doesn't allow me to erase. Oh, there we go. Nope. Guess I'm stuck with the pen here. Okay. So A double prime, right? So now we have, we're trying to double the angle, and you get these 2 points. So meaning that the rod person has another point to mark off, right? So the person stays there and they mark that point. Surveyor, let's see, and does not mark. And so the new mark, A double prime, is made, and the instrument operator given a sighting on the correct point midway between them, right? So those two have marks on the ground now, right? So you're trying to lay out that thing. So if I could zoom in, that'd be great, but I don't think I can. So a measurement halfway between them is marked off, and that's point A. So that's laying out. So that's actually marking on the ground, doing a layout is exactly that. So okay, case 2. Case 2 is where you want to be more precise than the least count of the object of the model. Will permit directly, well, better than you can just measure directly with the machine. Assume that an angle of 27 degrees, 30 minutes, 45 seconds is required in a heavy construction layout, and that a 1-minute instrument is being used. In other words, an instrument that can't read better than 1 degree, or 1 minute. Okay, the instrument, okay, in figure 5.8b. Yeah. Okay, the instrument is set up at and zeroed, set up at A and zeroed on B. So I guess I'll sketch that. It's clear. Try it again, or draw this other point. Okay, so the instrument is set up at A and is sighted in at B. Okay. And with an angle of is zeroed in at B with an angle of 27 degrees 31 minutes. Turn to whoa, yeah, that should be another sentence. But anyway, they turn 27 degrees 31 minutes. Turn to set point C prime. Okay. So back. This angle, 27 degrees, is turned to C prime. So again, that angle, 27 degrees, 31 minutes. Then, oh, I lost my case. The angle to point C prime is measured a suitable number of times so that the accurate value of that angle can be determined. Assume that the scale reading after 4 repetitions is, so they, okay, same thing, right? You turn this back, you hold, right? So you measure this 27 degrees off, and then you hold, sight back on B, so there's a prism there, and turn this again. So you got twice. In this case, they did it 4 times, and they came up with 110 degrees and 5 minutes. Okay. So I probably have to change the share settings on this. No, Let's just do screen one. Might be able to do this. Okay. No, guess not. Okay, so 110 plus 5 divided by 60, right? And then divide that by 4 because they took 4 times. So the average is 27 and change, right? So let's see what that is. So that's 0.5280, right? So times 60, that's 31.25 minutes, right? And 0.25 minutes is actually 15 seconds, right? Quarter of a minute, 15 seconds.
Yep.
Okay. I mean, I could go through the rest of the process here. Oops. Yeah, minus 31 actually. So there's the 0.25 multiplied by 60 again, and there's my 15. So 27, 31, 15 is our average of 4 times measuring it, right? So that's a nice way to do it. So
I can see it.
Okay, cool. Okay, so there I am. So that averages to 27 degrees, 31 minutes, and 15 seconds. So there. Yep, and that's what it says in the book. So that's nice. That's good. Okay, assume that the scale, okay, yeah, given a mean angle of 27, 31, 15 for angle BAC prime, in an excess of 30 seconds? Oh yeah, the original was supposed to be 27, 30, 45, right? So we're actually 30 seconds high on that, an excess of 30 seconds. If the layout distance of AC is 250 feet, okay, so down here, 250 feet, the point C can be located precisely by measuring C prime, a distance of C prime C, which gives me so they've established point C out in the field, but we know that we need to be, I'll exaggerate this a bit so I can draw it easier. So this right triangle here, yeah, this angle in this right triangle is the excess, so that's 30 seconds, right? And if that's 200 feet, how do I, so all I got to do is measure, I just need this little distance d, I guess, to find out the actual point C that I'm supposed to get. So C prime was measured with an error of 30 seconds. So what does that translate to in distance? And if I could measure that distance off, because distance measuring is a whole lot more accurate than angle measurement, right? So if I can just back that up perpendicularly, that distance on the ground, not a problem, right? So we can establish C with better accuracy than the total station can get you. Make sense? Well, let's solve this triangle, right? So if I have let me redraw the triangle, a little more exaggerated. 30 seconds, 250, and so what's X? Can we solve that triangle? The answer is yes, we can. And so,
Yes.
well, what trig function gives you You know, here's the angle, right? So this must be the opposite side, and this is the adjacent side, right? Because it's this is the hypotenuse, right? So identifying those, and then which trig function does opposite, and we have nothing to do with the hypotenuse here. So what's the what trig function does opposite and adjacent?
Sin?
Tangent, right?
Tangent, yep.
Yeah. Oh, that's what I thought you said, right? So what is it? Some old hag came a hopping through our alley, right? So yeah, tangent. So the tangent of 30 seconds is equal to x over 250. Right? So multiply both sides by 250. 250 times that. So x is what? 250 times the tangent of 30 seconds. All right. Good. So let's go back to the calculator. Pop that right over there. Calculator. All right, so how do you, this is not a great calculator for, can't change the size of it and stuff. But anyway, it's kind of small. 30 seconds, right? So 30 divided by 3600, and then take the tangent of it. Tangent in degrees, so that's tan d, is a very small number. And it should be, right? But I'm going to take I'm going to multiply that by 250. And so there I get in feet 0.03636 or whatever, right? So that's the distance I would measure perpendicularly to the point that we measured on the ground to get the actual point C. Right? Oh, that is what the book says, so that's good. After point C has been located, its position can be verified by repeating angles to it from point B. So I don't know how valid that, I mean, so who cares, right? I mean, you weren't be able to get it the first time, so if you put it at another point, at least you could verify that it's really close to it again, I guess. But it'd still be off. It still wouldn't measure exactly that because you're trying to measure it before that way. So anyway. Okay. That does get you better than what the instrument can do by itself directly. So. Okay, that's fine. I don't want to go over every single one of them. So let's see. We'll just go over the first couple, and then we're going to jump over to the resection, like actually getting X, Y, and Z coordinates out of these things, because that's a bit of a button pushing nightmare. So we got a handle on that, so we can go out in the field. That'll be our next exercise, is getting coordinates of points. So we just want to go over this, and maybe we can have some time out in the field of actually doing some of these exercises. I think I would like to do that. So it depends on how many people end up getting quarantined by the end of the semester, I guess. But we'll see. We'll see how it goes. All right. Okay, let's go over prolonging a straight line, I guess. So if I have a line and I just need to extend it, which often happens, this is how you do it, right? So basically, you sight back on, you set your instrument up at A. Okay. Let's go back to the whiteboard. Let's clear it. Let's put this up in the corner. Okay, so if I have point A over here, point B over here, I'm going to set up my instrument at A. Well, let's go over it. Prolonging a straight line, also known as double centering, is a common survey procedure used every time a straight line must be extended. The best example of this requirement is in route surveying, where straight lines are routinely prolonged over long distances and often over very difficult terrain. The technique of reversion, the same technique used in repeating angles, is used to ensure that the straight line is accurately prolonged. In figure 5.9, which I'm just sketching, straight line BA is to be prolonged to C, which is over here somewhere, right? So I'll just pretend it's right here. So that's C. That's the ideal. It's not on the ground. There's no marking on the ground at C, but there is at A and B. Okay. So with the instrument at A, a sight is made carefully. It's on station B. The telescope is transited, in other words, flipped over. So that's a nice fancy way of saying flip the scope over. And a temporary point is set at C1. Okay, so you set up your instrument at A. You're looking back at B. Flip the telescope over and measure off, and you're never going to hit it right. So there's C prime. Okay, so you mark off that. You put a marker where C1 is. Well, I said C prime, but that's okay. The book says C1. The instrument is rotated. Telescope is still inverted, right? So when you flip it over, it's now pointing towards the keypad, right? So it's inverted, as they say. But now you're going to rotate. Okay, this, you know, this is the vertical rotation. Now we're going to do a horizontal rotation back, right? Horizontally. So you're rotating the base, not the telescope. So now the telescope's still pointing in the same direction as the keypad, in other words, and you're pointing it back at B. That's the idea. Okay, then let's see. New sighting is made on station, and the telescope is flipped over again, and now it's pointing away from the keypad and it's in its normal position. A temporary mark is made at C2. So you sight back at B the second time after just rotating it along its base 180 horizontal degrees, basically, right? And then you're sighting it back, and you end up like maybe over here at C2 or C double prime. The reason for doing this, I don't know if it says doing that, or maybe it said earlier in the chapter or whatever. I didn't see it in here, but I don't remember where it is anymore. Any inaccuracies in, you know, flipping the telescope, like maybe the telescope, the bearings aren't, or a little worn or whatever, you flip it over and it might not be perfectly 180 degrees or whatever. It might be off a little bit as you rotate it. Off center, the axis of rotation is off center or whatever, and so you might be getting it off. So if you turn it around on the horizontal axis and flip it back over, you're actually removing how much ever it was off originally. So averaging those two basically gets you, you know, ideally that's what you end up with. So that's it. Over, okay. The correct location of C is established midway between the 2 points, right? So whatever you got between C prime and C double prime, you mark off, and that's your that's your measured C against the theoretical point C that you're trying to get with the steel tape. Over short distances, well-adjusted instruments show no appreciable displacement between points C1 and C2. Over longer distance, normally encountered in this type of work, however, all theodolites and total stations display a displacement between direct and reverse sightings. The longer the forward sighting, the greater the displacement. Note, When using modern instruments with dual axis compensation, the above techniques for prolonging the straight line can be modified with dual axis compensation. We don't have that on these machines, only one direction. So anyway, if you do have a double axis, like horizontally, like left and right and forward and back, axis compensation, the central processing unit of the instrument can measure the effects of the standing axis tilt and correct all the subsequent horizontal and vertical angles. So I guess a double axis means the horizontal axis and the vertical axis. So not just X, Y. It's not back, forth. It's just horizontal and vertical. Also, the surveyor can prolong the straight line by turning 180 degrees from the back sight to the forward station C. When this is done in both face 1 and face 2, in other words, away from the keypad and towards the keypad, inverted and not inverted, points C1 and C2 should be quite close together, thus confirming that the instrument has been calibrated correctly. So that's actually a method to calibrate. So far, so good?
Yep, sounds good.
Okay. Whew. Let's see. We don't need to. Well, a couple of these is good to do, I think. Maybe one more of these techniques, and then we'll skip over to the resection or the actual coordinate kinds of point location kinds of methods. So yeah, all of these are probably good to read. Maybe we should just assign that. I don't know. Anyway, let's do bucking in, where sometimes it's necessary to establish a straight line between 2 points that that are obstructed by something, a hill or a tree or just other obstacles, right? So it is usually permissible to find an intermediate position from points, from both points, that can be seen from both points. A and B are not intervisible, so point C is in an area from which it can be seen. The bucking in, also known as balancing in or interlining procedure, is as follows. The instrument is set up in the area of C at C1. And as close to line AB as possible. Yeah. So let's try this here. Just looking at this. So yeah, the way the book has it, we have point A over here, and it's on the ground. And the ground has a nice little hill, and then it goes to point B. So point A and point B are supposed to be laid out in a straight line, right? So we have point A, and we don't know where point B is. We have to lay that out. We have to put a stake in the ground at, in line with point A at some direction or whatever. So, well, you can put up an instrument here where you can see at least where B is supposed to be and where A is. So we set up at C. So here's the instrument at C. Okay. Well, actually, this would be called C1, right? Because there's no way you're going to put it right at exactly in line with A and B, right? So you can't know that. So that's C1. Okay, and as close to the line as you can get to estimate. The instrument is roughly leveled, so and a sight is taken on point A. Then the telescope is flipped over, and a sight is taken towards B. A line of sight will, of course, not be on B, but on B1, right? So like the book has it, in plan view, you would have A and this theoretical straight line to B. Okay. And C would be just slightly off of that, so there's C1 here, C1 on this point, and so really it's the dashed line. That would be fun to do, right? And you just flip the telescope over, and it keeps going, and you end up at, you mark off something at B1. The line of sight will, of course, not be on B, but B1, some distance away, noting roughly the distance B1B. Oh, I guess there is a point at B, sorry. How would you not know that? Yeah, you would have to know that, I guess. Okay. So we're just trying to locate a point C. So you don't want to, like, that's why you roughly level it in. So just as good as it'll measure. Noting roughly the distance between B and B, and then B and B1, and the fractional position of the instrument along AB. In other words, okay, so you got a triangle already here, right? So if this distance here is, let's say, 1 foot, and just to be easy, let's say C is halfway in between, right? So AC and CB are pretty much the same. Then I would measure C, I would move C this way half a foot, right? So that's what they mean by proportionally, you're moving C that distance towards the line AB, so that it can be set close enough to, well, let's see. And then you repeat the procedure. This trial and error technique is repeated until after sighting at A, the transited line falls on point B, or close enough that it can be set up precisely by shifting the instrument on the tripod top. When the line is being established, a point is set at or near point C so that the position can be saved for future use. The entire procedure of bucking in can be accomplished in a surprisingly short period of time, but all but the final instrument setups are only roughly leveled, and at no time does the instrument have to be set up over a point. Right? You establish the point after you get the instrument transiting, and you slide it on the telescope until it's right on, you know, the person at B, or the prism at B, and then you can establish the point right under the scope. Right? So you can use a laser, right? The laser will tell you where that point is, and then you stick a stick there and you got it. So that's fun. Okay, we'll skip the intersection of two straight lines, but it's similar to what we're doing here, right? You can average out your distances and stuff. So, all right. So prolonging a measured line by triangulation over an obstacle. That's pretty, I think that's an easy one to understand, so I'll let you read that on your own. Prolonging a line past an obstacle. Let's go to, before I get to 513, which is kind of the bread and butter part of this, I'm going to back up just a minute. And one thing, where is it? Yeah, section 5.4. I'm going to go back just to review, and because we've had some what do you call it, experience setting up, you know, putting an instrument over a point and stuff. Let's see how well we're doing after just kind of forging ahead with it. So just as a review, and see if we've developed any bad habits yet. Okay, not that you have. But. So I'm on page 117. Just going to look over some of these steps. We're going to place the instrument over the point with the tripod plate as level as possible and with the 2 tripod legs on the downhill side, if applicable. Right, so you don't want it unstable. So we've talked about that, I think. Stand back a pace or 2. This is what I kind of failed to. I didn't emphasize that much, but basically you can stand back and you can look at the point you're supposed to be over and whether the center of the tripod is visually kind of over it. And then you can stand 90 degrees to where you're looking there and see if it's over that. So you can kind of get over that pretty easily. So stand back a pace or 2 and see if the instrument appears to be over the station or, you know, stake in the ground or wherever. If it does not, adjust location and check again from a pace or 2 away. Move 90 degrees around from the original inspection and repeat the steps. Yeah, it seems to me you could just look through the hole, but maybe a lot of times we're setting up the tripod a little low, so maybe it's not so easy to look through it. I don't know. It seems to me that looking through the hole is actually pretty quick. Anyway, check that the station point can now be seen through the optical plummet or that laser plummeted spot is reasonably close to the setup mark. I guess they're assuming that you already have the instrument on the tripod. So I guess if you sight that in, I don't know. Yeah, maybe it's after you place the tripod and get it pretty level and then put the instrument on it and then you take a step back. So that makes sense. Did I skip that part? Anyway, I guess they were assuming you already have the instrument on the tripod. And so you take a step back after you get it on the tripod and it's pretty level, not that you spent any time leveling it, but the simple act of eyeing in the instrument from 2 directions 90 degrees apart takes only seconds, but can save quite a bit of time eventually. Check that the station point can now be seen through the optical plummet or that the laser plummet spot is reasonably close to the setup mark, then push the tripod legs firmly into the ground with the shoe spur there. If it's in soft ground, just got to get it set nice and, you know, most of the time we're on this carpet or inside or outside and stuff, but on the grass or something, just want to make sure that it's not going to sink any further if you hang on it with, if you're balancing yourself on, holding the tripod as you're working, you might actually put it off center or off level. While looking through the optical plumb or the laser, manipulate the leveling screws until the bullseye of the optical plummet is directly on the station mark. I think that's a typo. Level where we should be just sliding it on the tripod base to get it over that, because it should be leveled at that point. Level the theodolite circular bubble by adjusting the tripod legs up and down. This is accomplished by noting which leg, when slid up or down, moves the circular bubble towards the bullseye. Upon adjusting that leg, either the bubble will move into the circle, the instrument, or away, or slide until it's exactly opposite another leg. That leg should then be adjusted up or down until the bubble moves into the circle. If that bubble does not move into the circle, repeat the process. Okay, so yeah, it's not the only way to do it, but what they're saying, I really don't like that idea that much. But they're saying that you're going to level the with the instrument on the tripod, you're adjusting the tripod legs with the instrument on it to get the bubble level on the instrument in the center, and then you adjust the screws. Okay, that leg, okay. If this manipulation is done correctly, the bubble will be roughly centered after the second leg has been adjusted. So it is seldom necessary to adjust the legs more than 3 times. Comfort can be taken from the fact that these manipulations take less time to perform than they do to read about, I guess. Perform a check through the optical plummet or note the location of the laser spot to confirm that it's still close to being over the station mark. Turn 1 or more leveling screws to be sure that the circular bubble is now really centered. Loosen the tripod clamp bolt slightly and slide the instrument over the top, over the mark. Okay, retighten the clamp and then reset the circular bubble if necessary when sliding the instrument on the tripod. Do not twist the instrument, but move it in a rectangular fashion. This ensures the instrument will not go seriously off level if the tripod itself is not close to being level. So in other words, if the tripod base isn't quite level and the instrument itself is accommodating for that off-centeredness, if you rotate, if the tripod, you rotate that, it's off like this and you rotate it, you've just put it further off level. So. Nice. Okay. So good. Let's see. Is there anything else to say about that? So then it goes to the tubular bubble, which we already kind of talked about. So just turning it every 90 degrees. Maybe I should just read it anyway. The instrument can now be leveled precisely by centering the tubular bubble. Set the tubular bubble so that it is aligned in the same direction as 2 of the foot screws. Turn these 2 screws together or independently until the bubble is centered. Then turn the instrument 90 degrees, at which point the tubular bubble will be aligned with the 3rd leveling screw. Finally, turn that screw to center the bubble. The instrument should now be level, although it is always checked by turning the instrument through 180 degrees. On instruments with dual axis compensation, final leveling can be achieved by viewing the electronic display and then turning the appropriate leveling screws. This latter technique is faster because the instrument does not have to be rotated repeatedly, so that's nice. But we don't have that, so. All right. Whew. Should we take a break? It's been about an hour. Let's take a quick break. I'm going to drink water. And then we'll talk about this resection kind of idea that I want to talk about. So.
Okay.
All right. Let me pause the recording. Okay, so if I have 2 points, 3, 8, and 11, 2, I can make a right triangle between them. Let's see, maybe. So here's a right triangle, right? The hypotenuse would be the distance between them, and it wouldn't be curved. Let me undo that. Can I draw a straight line? Would that be nice? No, I can't. Thank you very much. Okay. Oh, trying to rotate this tablet. Okay, I shouldn't have erased it. Go this way. Okay, there's 3, 8, right? Okay, so again, we have, we know the distance here is 1, and we know the distance here is 3, right? Went from 8 to, no, the other way around. It went from 3 to 11, that's 8. And it went from 2 to 8, that's 6. Right? So technically, this is called the latitude, and this is called the departure. Now, I know latitude's used in another, when you're talking about latitude and longitude, but it's sort of similar, but basically that's your delta north, right? That's how far you went in the north direction. It's actually -6 in latitude if you really want to think of that, because I went from 3, 8 to 11, 2, so I have a positive departure and a negative latitude. So there you go. So as far as my azimuth goes, okay, so I get the distance of that. So what's the distance? Wouldn't that just be the square root of -6 squared plus 8 squared? Wouldn't that be equal to 10? 36 plus 64 is 100. Square root of 100 is 10, right? It's a 3, 4, 5 triangle. Isn't it? Yeah, right? We're good? Okay, so the distance is 10. And so what's the azimuth, right? Well, it's really, if I put the north arrow on there, like a compass on there, there's north, it's the angle that it turns with this. Okay. So, couldn't I find this angle? Take 180 minus it? Maybe. Okay, what's this angle? Now I have 3 sides, but this one I used math to get, and it may have some rounding error. I mean, in this case it doesn't because it's just a 3, 4, 5. So it's exactly whatever, but you would definitely use your departure and latitude here. So opposite side, so that's my opposite side, here's my adjacent side, right? So again, tangent, right? So the tangent, oops, of my angle, let's just say that's alpha, for nice Greek letters, make it sound smart, is equal to 8 over -6. And I'm keeping that negative for some reason. Let's just see. Okay, let's figure, so what do you do here? How do you do that? I could reduce that triangle, but it doesn't matter. I mean, I can still type in 8 just as fast as I can type in 4 and 3. Okay, so how do you solve it for alpha? I want that angle. How do you get rid of tangent? Divide by tangent? No. Tangent's like a square root. I don't divide by square root to get rid of the square root. I square it, right? So what's the opposite of tangent? On the calculator, it's usually written as an inverse tangent.
Yeah.
You know what I mean? So if I take the inverse tangent of one side, I have to take the inverse tangent of the other. And so these kill each other, those undo each other. And so alpha is equal to the inverse tangent of, okay, 8 over -6. Okay, what's that equal to? Still got my calculator. Pop that over here. Clear it. So you have the inverse. Different calculators are different, right? So I'm just going to do 8 divided by 6, and I got to change. I do want to change the sign. There it is. There it is. -8, and then take the inverse tangent. Or is it? There it is. A tan of all that, -53 degrees. Okay. Yeah, what is that? So here, I'll keep that there. Let's go back to the sketch. Okay. So this angle is 53 degrees. Point something degrees. Okay. So what's the azimuth? So what's this over here? Isn't that, shouldn't that add up to 180? So if I take 180 minus that 53, whatever, degrees. We're okay with that so far?
Yep.
Okay. So in this case, it's negative, so I'm just going to add 180. There we go. So I'm going to subtract one, I got to get degrees, minutes, seconds out of this thing, I suppose. But either way, that's the azimuth, right? Minus 126. And multiply that by 60, so it's 126 and 52 minutes. And multiply that by 60 again. So 126, 52, and 11.6, right? So using coordinates kind of gives you the false sense of security as far as like how many decimal, seconds can I really go down to, the 15th decimal place on seconds? That beats a total station by forever. So no, you probably can't. Depends on what you use to measure that, but yeah, you're going to have some least count stuff going on. So I'm just going to say, 11.6 at best. That's way better than it. Most machines anyway, right? So, all right. Okay, yeah, what did we say? What did we say it was? 126 degrees, 52 minutes, and 11.6 seconds. Is the azimuth. So just knowing the two coordinates, and that's just the x and y, right? So what could I do? What else could I do here? So I know the direction between those two lines. Can I know the slope between them? Well, if I had the z coordinates, which you can, right? Because the total station can measure angles vertically as well. So so it's important to get the height of the instrument, right? So this is how do you do that? Probably the most convenient way is put your machine over a known point, right? So a benchmark of some sort, some other established marker that has an x, y, and z coordinate on it, and then measure the height of it just with a tape measure, right? Measure its height above that point. And that gives you its elevation, the height of the instrument. Once you know those, then you have the x, y, and z of that point. However, it may be necessary that you do something called resection. Okay, resection is a process of finding the coordinates of the total station of the instrument when it's over a point that you don't know, right? Or you could just put it out. So our exercise that we're going to do is, should I just go back to screen? Yeah. Use Google Earth. Turn that off. Wait a minute. Wait for it to start. Drag it over. So on Monday, today's Wednesday, yeah. Monday, hopefully there'll be enough people here that we're going to go out and we're going to go to the lawn right here. So we're over here in the lab. So if we come down here to the lawn, which we're kind of familiar with, we're going to get some, I have some of these corners. I have some known locations already mapped out, okay? I think I have one back here and right here and right here. So if you put the total station out in the grass somewhere and then you shoot to, you aim at a couple of these points that you know, like we'll have one over here. So if I have the machine out where the cursor is here, then I can zoom in, or I could sight in on this, and then I could sight in on that, and it's going to measure distance, right? And the angle. So distance, it's going to get a 3D coordinate of where that station is. So it's going to get the height of the instrument. It's going to have, because we'll know the height of the prism, right? You got it. Those poles the prism's on are 4 feet, right? And then the prism's an extra so and so feet, right? Like maybe 1/10 of a foot or something, right? Well, that'd be 1/12 of a foot is an inch, right? So a couple twelfths. Okay, and then you'll sight in on those points. So how do you do that, right? That's what I want to talk about. That's called resection. This technique permits the surveyor to set up the total station at any convenient position, sometimes referred to as a free station, and then determine the coordinates and elevation the X, Y, and Z, with an N, E, and Z, northing and easting is usually what they call it, of that instrument position by citing previously coordinated reference stations. When citing only 2 points of known position, it is necessary to measure and record both distances and the angle between them. So if I only did like this corner over in the corner of the building and maybe this corner of the sidewalk, then I'm going to have to measure the angle between them, and that way you can solve the triangle, right? So if I have those two known locations and the distance between them, then what are you getting, right? I just got to practice my sketching, so I'm gonna have to bear with me here. Okay, so I'm going to sketch that again. So here's a point that's known, so I'll call that point A. And just like over here, this would be point B, and that's known. And then you just put the instrument here that's unknown, right? So if I know the location here and I know the location here, then I'm going to measure that distance only. Well, right, that's all I have is I can just measure the distance. I don't know direction. I don't know where this point is, so I can't get the azimuth between those 2 points. I got nothing, right? All I can do basically is measure that distance, which means I just know a circle. Oh, that's not a circle. A circle centered at A, right, from there. And if I do that to B, right, then I'll know a circle, right? So where the circles intersect would be where the station is, but there's an ambiguous point here. So it's not, it's pretty close to a solution, but unless I know this angle, that gives me the third piece of, you know, I'm trying to solve an equation with not enough, with too many unknowns. That angle gives me enough to, well, solve the triangle, basically, right? So if I just knew, so yeah, if I think of the triangle, you did this in geometry class probably. So if you knew, so I know the distance here, right? So this would be little c and this would be big C. I think that's how you do it. And then little a opposite of big A and little b opposite of big B. I know A, B, and I know the coordinates, so I know C, right? But that means the triangle, if I know those two distances, that could solve a triangle. That could solve this triangle too. Let me put a different color. This would be the ambiguous solution. Forget that line. No, that's great. Anyway, that triangle also satisfies all that that solution too, right? Because little this is little a right here, and this is little b right here, or C. Well, yeah, that would be B, and that would be, that's actually B, and that's A, and then C is still C, right? So that's the ambiguous solution, unless I know this angle, right? So with that angle known, then I can, the instrument can solve it, right? Mathematically, that's enough to solve the equation. But in most cases, a third point is better. So you can just get another, you can get another point, and that allows for a little bit of statistical error correction. So it's better to get at least 3 points of knownness, right? 3 known points to establish the northing, easting, and elevation of C. All right. Actually, just shooting 1 point will get you the elevation at C, the height of the instrument, because you just have the distance and the angle. So you have this vertical angle and the distance, and that's fine. And you also have the elevation at A, so you can just add that up. But, and you can put the rod height or the prism height. You have to put the prism height in there. So this leads us to the next little section here where we have to figure out how to do that on the total station. It's a little tricky. So, but we know what we're doing, right? So we're measuring. We're not just measuring distance. We're making the machine do the calculation. So we don't want to have to like take it back and just take those measurements and whatever and then find out what C is. We need to know what it is out in the field, because what are we going to do with that, right? So the next thing to do is find other points out there, right? So I can't go back to the office yet till I get those points that I have to measure. So let's say there's a point over here, and so I just turn the instrument and I point it at C, from C, and I get D over here. This got all thick all of a sudden. Okay. That's better. All right, with that? Okay. So let's look for on the server. I can put this on Canvas too, so you can take a look at it and kind of look through the owner's manual, right? This is the electronic owner's manual for the newer total stations. Okay, so there it is. Okay. You can see that, Nate? Are we good?
Yep.
Okay. All right. So when this is a process of measuring distance. So the atmospheric conditions, the pressure and the temperature, need to be recorded, as well as setting the prism height and the offset, right? So those things have to be done as well. Okay. So let's look at this. We've already gone through angle measurement. It's great. Distance measurement. We've already done coordinate measurement. Setting coordinate of values of occupied point. Well, that sounds like it's pretty good, right? But that's not what it's saying, I don't think. Right? So set the coordinates of the instrument, the occupied point, according to coordinate origin, and the instrument automatically converts and displays the unknown, the prism point coordinates following the origin. So that's the idea after you get the coordinates of the known point, right? So the other thing that we can do is put the instrument over a known point, right? And then sight it in at another known point to get its elevation, right? So its location is already set, but it's you know, the direction it's facing is not, right? So it still has that angle ambiguity. So you have to point it at like a known point to get another known point will get you the direction it's facing. And then once you can find out which way it's facing, then you can point it at anything else and get its location. It's X, Y, and Z. Does that make sense? Sort of. Okay, we'll run through it. I mean, it's kind of tricky. So this is what we want to be able to do, is find an unknown point, but we have to know where this station is and what direction it's facing. So that's the idea. So that's where we want to end up being. But before we can do that, well, let's actually run through this, because this is the end goal here, right? We're going to set the coordinate of the instrument, the occupied point, according to the coordinate origin, and the instrument. The coordinate origin could be like the state plane coordinate system that we've talked about before. Or, I don't know, does this thing set up units? Can we work in meters on this thing? I would imagine you could, but let's see, units. Huh. I don't know that you can change the actual measurement units. I think it's all in feet still. Seems to me. All right. Anyway, back to chapter 5 here. Where was I talking about? So we want to get the coordinates of where the prism is on the point that the prism's sitting on. So this is, if you knew your occupied point's location, then you have to tell the machine what it is, right? So you can do that by resection, or you can just type it in if you knew it. Like if you went over a known point, you would have to just type that in. Does that make sense? So this is what you do. You get the key and you go to do the coordinate measurement mode. I wonder, I could probably sign in on my phone and show that. Yeah, let's try that. Should have enough power for this. Okay, so now we know that the total station can measure coordinates, right? But first you have to set where it is and where it's facing. Okay, so that was chapter 5 in the manual. Let me go back to chapter 5 now. There we go. Okay, so basically just looking at, let me try leaving my Zoom meeting here. That's okay. Okay, so what we did is once you hit the that axis key or the NEZ key, the 3D key, so where you get the NE and Z, it'll start measuring right away for you. So all you have to do is column 8 on a prism, and you got it. So how do you get that coordinate though? When you put the machine out there in the grass or whatever, you're not going to know its coordinate. So that's where chapter 12 or something. Let's look at the table of contents here. No, that's not it. Da, da, da. Here we go. Setting a new point, resection method. Here we go. Sorry. So it's in chapter 8. Okay, we're going to set up the instrument at a new point and calculate the coordinates of that new point using the coordinate data of maximum of 7 points, but a minimum of probably 3. Okay, you can do 2, but you should do at least 3. So this is how you do that. And we don't have to hit all the keys. That was a little disconcerting, I guess. But anyway, so we're going to go to layout mode. Maybe I should do the keys here. Yeah, I think I should actually. Unfortunately. Let's just see. Level that up a little bit more. That's pretty close. It's just that screen is so hard to show. All right. So in this mode, that's not going to happen. So I think if I go to the menu, yeah, so I push the menu button, and then I need F2 is layout, and then as the let's see. Oh, yeah, it's asking for a file, a layout file. Select a file. We can skip that. And then this is our layout menu. So in the layout menu, we want to occupy point input, right? No, we want to page down, sorry. And new point, right? So F2. So every page you're going to have. So there's a new point. And we're going to pick resection, right? So F2 for resection. And point number, input, and then, I don't know. Point 12. Okay, there's point 12. And it may be a point that's in sequence of another point, or maybe just out of sequence. So maybe you have some more digits, like 1, 2, 3, maybe. Okay, so enter that. So I have point 1, 2, 3, and the instrument height, again, we would enter that, so that's good. And then, so we're going to shoot a certain point. Again, we're just going to hit the the northing, easting, and elevation of the known points. It'd be nice. In fact, I have a sheet. So we're going to do this. I have some known points out there, and we'll go ahead and input those from a list. Let me escape out of that. Yeah. So we're going to do resection again. And in this case, new point. Let's do point 33. How about that? Okay. And then instrument height, that's good. And so this is point number 1 that we're shooting, and we can pick it from a list, right? Well, we don't have any list, but if we develop the list in the class, we can just pull that list up, so we don't have to do a bunch of typing in the class. I mean, out in the field. We can just pull those points from the list and say, okay, I'm on point A or point 2 or whatever, and we'll do that in class on Monday, to get those in there. Okay. So after we go through this part of resection, then we'll know where this instrument is being, where it is in the world, and then we have to orient it. We have to actually get an azimuth, so we know what direction it's facing, and then after that we can shoot a bunch of points with their NEZ coordinates. So that's the idea, and that's the plan for Monday. Sound good?
Yep, sounds good.
Okey doke. Stop that. Turn that off. Okay, well that's good enough, I guess. So any questions, comments? We're good? We're what?
I'm good here.
All right, so yeah, on Monday we'll add these points from into a file on the total station, set the atmospheric pressure and the temperature for outside, and we'll go out there and we'll measure some stuff. So
Okay, sounds good.
well, yeah, so we'll have somebody carrying a phone, I guess, maybe. And if it's just Garrick, I know Camry's being quarantined also, and I don't know about Noah, but if there's Noah and Garrick, we could make this happen, and
Yeah.
you'll see everything. So
Noah uses his phone anyway, so.
okay, yeah.
Alrighty. Alright.
All right, well, have fun.
Alright, thanks. Alright, bye.
See you later.